Hello everyone, we're back today on CodeForces round 881. This is a Division 3 round, so it's not rated for me right now. We will try to solve all the problems. I think the last time we did very well. You can check out the other videos on my channel, and as well I do explanations on programming and electronics, so there are a lot of things that we went through, and we do sometimes live streams as well, so that's kind of cool as well. Yeah, now 27,000 people here. I hope the problems will be nice. So first problem, such an array coloring, found an array of n integers. You have to paint each element of the array. You can use as many colors as you want, but each element should be painted in exactly one color. And for each color, there should be at least one element. So the cost of one color is the value of the maximum S and minimum minus minimum S, where S is the sequence of elements of that color, and then you need to paint the maximum possible cost of coloring, and now you can probably choose any number of colors, yeah, so if it's n is even, we will, so if n is even, we can, so we'll need to sort them all. I will sort them all here. And then so the answer will be equal, actually the answer can be as well int only, because there won't be overflow, but n-half elements the first n-half elements would make the answer, we will minus that, and then the last n-half elements we will add them. To print out the answer. Okay, this passes, so I will just submit that. Let's go. Okay, gets accepted. Let's go to B. So there's today Alex was brought the array of n integers. He can apply as many operations as he wants. In one operation, he can choose some sub array and multiply all of the elements with -1. So he can just invert the size. Okay. Alex is late to school, so you should help him find the maximum possible sum of numbers in the array, which can be obtained by making any number of operations. So we can just, for each, like with these elements, we can just invert them. What do you need to print? For each test case, print the maximum possible sum of the array and the minimum number operation to get the sum. So this is pretty straight. Is it straightforward? Is there some trick here? I don't think so. I mean, probably you need for a bigger formal proof why a greedy solution here will work. Actually, I'm thinking something here. Actually, no, greedy won't kind of work. Or will it work greedy? Let me just think for a second. Yes, greedy will work, and I have a proof for it. Okay, so let's just okay, so there's like count, and then there's the answer. So the answer is pretty like, okay, so this is the idea. So we will only break if a of I is a positive number and a of I minus 1 is some negative number. No, actually we will do this. So if a of I is positive number, then if I have a negation, I will get the count plus plus, and at the end, actually, I will probably just push a positive number at the end. So I will push back like 1. And then just for auxiliary purposes, also the answer will be just absolute thing. So if this is the count plus plus and then negative is false, also if it's not a negative number, we just continue. Else, so if it's a smaller number, if it's negative number, then we'll just continue. If it's not a negative number, we will do a negative number here. Also, count if it's not if a of I is smaller than 0 and it's not negative, then this. That was kind of slow, I think. I think B is. So CodeForces is lagging something. I'm just going to use CodeForces. Okay, so I got back. This still hitting. Okay, whatever. So C. Vanya really. Okay, so we got acceptance B. Vanya really likes math. One day, when he was solving another math problem, he came up with an interesting tree. The tree is built as follows. Initially, it has one vertex. Then Vanya adds 2 children to it, adding consecutive numbers. After that, he will add children to the vertices in increasing order, assigning their children the minimum unused vertex. So this is like a binary tree, I assume. So yes, it's a binary tree. Vanya wonders what is the sum of vertices and numbers from on the path from the vertex 1 to vertex with number n equal to. So this with number n equal to, because we this has, I have seen this problem somewhere else, So the idea here is just to do some a bit mathematics, but this here, when we get this n number, while n is bigger than 1 than 0, so sum plus equal n divided by 2, I think I would guess something like that. Because this is in log n time, it would work. Surely should work. Gets accepted. Okay, let's go to D. He has an apple tree growing in his garden, rooted tree of n vertices. The tree is very unusual. It grows with the root upwards. However, it's quite normal for the programmer's tree. Okay, whatever. Let the apple now be at vertex U. So apples will grow in certain vertices. After the apples grow, Timofey starts shaking the tree until the apples fall. Each time Timofey shakes the apple tree, the following happens. Apple now at vertex U. If vertex U has a child, the apple moves to it. There are several such vertices, can move to any of them. Otherwise, the apple falls from the tree. So if it's apple on the leaf, it can be shown after finite the apples will fall. He has Q assumption in which vertices apples can grow. He assumes that apples can grow in vertices X and Y, and wants to know the number of pairs A and B from which the apples can fall from the tree, where A, the vertex from which the apple X will fall, and B, vertex that which Y will fall. So this, for the first assumption, there will be two possible pairs of vertices. The first assumption is 1 and 2. Wait. First example, first assumption is 3 and 4. Okay, so yeah. So here the idea is that the apples are, as I assume, they are independent. And then when they're independent, what we need to do is just for each of these, we need to see how many leaf nodes. So for each node, we need just to kind of know how many leaf nodes it's like down. So, you know, so in his subtree, how many leaf nodes there are. So that's what we need to know. I will just, so let me just check. Okay, so that's fine. We are recording. Okay, just I want to check here. Okay, so for, we read the tree, of course. We push connections. Pretty straightforward problem. Like the problems so far. I like the problems because the problems are educational. So I will just root. I will just get the, just do a DFS here. So if adjacency at u.size is equal to 1, so if it's a leaf node, we just return 1. Otherwise, we do some like sum here for each vertex, for each child of u. If v is equal to the parent, we continue. So for each child, we're just going to sum up this here. Also, I need to know like leaves here. So we're gonna sum up and then we're gonna say return leaves at u is equal to the sum. So this is like we're counting what leaves it is. Also, we kind of need to clear, and also we need some queries here. Just really quickly, just write some queries. Yeah, so we write some queries. The queries are just the output is leaves at u times leaves at v. That's the output. Apparently that's not the output. Wait, that is the output. 3 and 4. Zero, 0, which means something is wrong. If adjacency clear resize. Adjacency am I reading something wrong here? Oh, because it's the root node, of course. P is not -1. But can the tree be only with one node? No, it can't be the tree. Tree can't be only with one node, so that passes. Submit. Here long is needed because the combinations of the pairs are could be very large. Let me open what is now. Okay, E. You're given an array A consisting of n zeros. You're also given a set of m not necessarily different segments. So each segment is defined with this and represents a subarray of the array. Let's call segment Li or I beautiful if the number of ones on this segment is strictly greater. The number of ones in this segment is strictly greater than the number of zeros. Okay, you have Q changes. For each change there will be an assignment. You have to find the first change after which at least one of the m given segments becomes beautiful, or report that none of them are beautiful after the Q changes. So okay, so this is a really cool problem. This is a really cool problem. So the segments are really big, of course. So this variable problem. So what happens on a segment that there is like, let me just open up Node. What happens on this segment is so we have many zeros, and then you turn into one. What about if I apply like all of these queries after like, actually like what I will do is I will take a look at the problem differently. So I will apply all of these changes, but each change will be actually like one of so each query will actually be like, so first you have like this array, and then when we assign this to one, there will be like one here, and then there will be like, let's say 2 here, there will be like 3, 4, 5, 6, like that, and 7, let's say, and then 8. And then what we want to do is that like we want to query out, so for each of these m intervals, I want to query out in this interval what is the median in this interval. So what is the like the n half number in this interval, so after sorting, of course. So this could be done multiple ways. But there is a way to do it with kth order statistic. This is kth order statistic, but I had a better, I mean, we could do it with square root decomposition, right? But I already have that. I already have kth. Let me just think about this, right? So we want the median, we want on these ranges, we want the median element, right? Is there a better way of thinking about this problem? So kth order statistic is a very well known. There is this kth minimum segment tree. I will use this. This is from actually like from Geeks for Geeks. This is the kth minimum segment tree from Geeks for Geeks. So kinda fine to use that. I will. So let me just see how the input is constructed. There is n and m, so n and m. there are these m segments, so like I will just construct an interval here. There's probably like a easier solution than this, but whatever. So intervals, this. And then we want to read all the Q queries. And then at this ID we'll do like A at this ID is I plus 1. Or just I, it's fine, it's enough. Okay. And then we need this kth minimum segment tree on A, and then tree dot, wait, is it built by default? So it's built by default, so for each of the intervals, for each of the m intervals, there will be an answer here. For each of the m intervals, we will query out, so this is like the median is tree.query the starting position, the ending position. Let me see how I used here this. I used it here. So this starting ending position is what? So this is by default here. N is tree.n minus 1, then here it's start n and then k. So this here is L r minus L plus 1 divided by 2. Here this is L, this is r plus 1. Okay, and then but if the intervals here, by default the intervals are all zeros, so by default we need to put these intervals to int max or something like that. So if it's int max, it's going to be this. If it's otherwise, it's going to be the answer, something like that. Now L mine actually like that. kth smallest element in L are this. Is this correct? So the size of the interval, if the size is 5, there will be like the third element should be catched. So if the size is 5, then there should be like the third element catched. So here doesn't kind of make sense, but let's print A here. Let's print okay, so we have like this. So this is the 0th query, this is the 1, the 3, 4, and 5. So 4 and 5. 1, 2, 3, 4, 5, okay, whatever, but doesn't matter. But here, what is L, what is R, and what is median here? From 0 to 1, that's not correct as well. The kth smallest element in the range L to R. How have I used this? Oh, I see. I need to do A at this. So 3 and 4. Three and 4 here. 3 and 4, but what was the is strictly greater than the number of zeros. Strictly greater. So that means it's not the median, but it's like one above the median. So that's +1 or something. Oh yes, here it's okay, that kind of works, so I'll just submit it. That should work if the tree is coded well. Okay, it passed a lot of cases, so now here F1. So this is the simple version of the problem. The only difference is between the simple and hard version is this version is that U equals 1 and the hard version is what? Take any possible. Okay. As is known, Omsk is the capital of Burland. Like any capital, well-developed metro system. Metro consisting of a certain number of stations connected by tunnels, and between any two stations there is exactly one path that passes through each of the tunnels, no more than once. In other words, the metro is a tree. to develop the metro and attract residents, the following system is used. Each station has its own weight, so it's either -1 or 1. If the station has a weight of -1, then this station is visited by the Omsk resident. A fee of 1 burl is charged. If the weight of the station is 1, then is rewarded. Omsk Metro currently has one station with number 1 and a weight equal to 1. Every day, one of the following events occurs. A new station with weight X is added to the station with number VI, and it is assigned a number that is greater than the existing numbers. So this is just like adding a child, right? Alex, who lives in Omsk, wonders, is there a subsegment, possibly empty, of the path between vertices U and V, such that by traveling along it, exactly k burls can be earned? If k is negative, this means we'll spend on travel. Okay. In other words, Alex is interested whether there is such a subsegment of the path that is sum of the weights of the vertices equal to k. Note that the subsegment can be empty and the sum is equal to 0. You're a friend. Your task is to answer Alex's questions. So there is like an addition of this, and there is 3 numbers, u, v, and k, guaranteed that the vertices u and v exist. In this case, it is necessary to determine whether there is a subsegment, possibly empty, of the path between stations as a sum of weight. So given an array, is there a sub? So given an array, is there a subsegment? So we will solve F2 here. We'll try to solve it. Is there a subsegment? So given an array, is there a subsegment equal to k? Okay. So I have some array. We'll take a look at this level. So I will take some array. And the query question is there a subsegment such that like the sum of AI equals to k? But it's very weird why it's like just only -1 and 1. So it's kind of only like just traveling just a little bit and just like down. It's not like all the possible values, right? So if that would be the case, you could iterate by this here guy and then say then for all of these here on the end, is there such k so is there such a prefix that k is equal to, so is like you would go into the map and ask for like k minus so no, this is the, you have one sum here, so this is like prefix I, let's say prefix I. So we want to ask, is there, so we want prefix I is equal to some prefix j plus k. And we have prefix I, we don't have prefix j, so prefix j will be equal to prefix I minus k. So essentially you would ask into the map, does pi minus k exist? And if such exists, then you know you know that there is such a subsegment in this path. And this is kind of this F1 is solvable in this way. Just but there is another problem, right? So you would just iterate, and this is like for one question. But now you have a lot of questions, and now you have a lot of queries. Well, how do we deal with that? Wait. Five people solved it. I mean, how do we deal with this? So there will be like at most, so when you go down the tree, there will be the changes that from vertex U to vertex V will be created, will be at most n changes. So there's like this and this. So do we just say the minimum and the minimum reached and the maximum reached? And is there by definition a separate that will like, so yeah, so from this point on here to this point on here, you could construct any such subset. So this is the idea. So the idea is very simple. We can solve it. It's just the minimum and the maximum. That's what we need. And this addition of things we could just make it such that like it's just heavy light decomposition in a sensible way, right? So there is like Q. First I will construct the tree. So I want some heavy light decomposition, HLD. So this is the HLD. Actually, do I need? Can I just use my own segment tree and not this here? Because I will never. Yeah, I can use my own segment tree here. I'll never lazy update anything, so just change a few things here. So I need minimum and maximum. I kind of don't need the value, but I can just get away with this. I will just offset it, right? Yeah. Okay, so this is the segment tree. I will here define some ideas here. Define some things useful. I will need to update something here. So modify path. So query subtree, I don't care. Modify path is like just modify vertex. Modify vertex is just position tree, put position at U. Now the value is what? The sum of this. Then query, we need to return like minimum and maximum. So we just kinda want to return minimum and maximum. So this is minimum query from L to R. Then there's Q queries. So we're gonna just save queries that are question marks. I don't see how this is wait, VI Yeah. So I just need the question marks are just so there's like U, V, and then there's K here. So if there's plus, I want so I want to have like vector adjacency matrix, and in this adjacency matrix I will have some U and some value. JCU pushback. So the last node is 1. So I just U node plus plus, and then the value of this node. So the value of this node else queries that pushback. And this is going to be like that. So okay, we push the queries. So we kind of build here we build the tree. Here we assign the values to each node. Now the trick is to build this this HLD, so this structure false. So this is like not on edges, so on vertices. So this HLD, we just push this adjacency matrix to it. Now the adjacency matrix kind of has to be full, so kind of has to be full, I think. Actually, no, right? So no, doesn't have to be. Yeah, because it's only going down here. Okay, so modify vertex. So we have to modify each vertex separately. So we kind of have to go through each vertex. You kind of have to go through each vertex. So values here is 1 in the first vertex. So we go through each vertex and we say HLD modify vertex and then I and then values of I. This will add each value, and then we kind of want this to do these queries. So we want for each query, so U, V, and K, we want to see if this want to query the path. So pair here, pair is HLD dot query path from U to V, and then you know this pair that first is like the minimum and pair that second is So this is minimum and this is maximum. And now the difference between minimum and maximum. So first we need to know actually like the values here. It's not at this node, but it's the values at u plus the values at val. Okay, so this is like prefixing, and here we need to prefix minimum and maximum with the, so minimum is values at the parent of u, so parent of u, the parent here is so values at the parent of u, and if HOD if u is, so if u here, if u is not the first node, and the same thing we so we kind of wanna first know what is the, if depth, if HOD dot depth at v at u is bigger than HOD dot depth at v, then swap u and v. This is what we want, and here we want as well the maximum to be this, and then if mx minus min plus 1, so is it plus 1 or is it not plus 1? So let's say the mx is the minimum here we found is let's say 1, and then the maximum, let's say, is 3, right? So what you can create is you can create you can so let's say it's something like this. This is maximum, this is minimum, this is maximum. This is u and this is v. You can kind of get from u to the minimum if we're offsetting u as like this is 0, so we can kind of get to the minimum. We can kind of get to the minimum. Also, we can kind of get to the maximum, to any of the maximum here. But can we get more than the... We can start here and get all the way to the maximum as well. Or we can start here. We can start here and get all the way to the minimum as well, right? Such as the sum. Right, this is prefixing, so this is says that like to here we have been I'm pretty sure it's something to do with the minimum and maximum of this path. So the minimum goes here, the max. We can reach the maximum. We can reach the maximum minus minimum as well. But can we reach? We can reach everything in this range because we can take anything here, but also can we reach also if I start here I can reach the maximum, right? I can reach anything maximum, and how much to the minimum can I reach here? That's my point. So if I start here I can reach like that to the minimum, right? But wait, if I start here I can reach we can reach a lot, right? How much time we have? So this vertex minus we can definitely reach maximum minus minimum plus 1 or something in the, so k should be definitely smaller. So if minimum is like -1 and maximum is like 3, 3 minus -1 course 4 here. So we can start from -1 and reach all the way to 4 here. Yeah, that's one. That k is fine. That k is possible, but also like k has to be so k has k has to be bigger than something. So k, you cannot reach. So what if there was this position? So there was like some maximum, then there's some minimum here and like that. So can you reach this maximum is the problem. Probably not, right? Like let's say this is 0 and like that. So let's just like this, draw it like that. So you can reach here, but you fall down. Fall down. Now technically you can reach the negative now, the whole negative portion here. But you can reach the whole positive portion since this and this is the maximum here. You can reach this here, right? So it's like all of these be the maximum number you can reach is equal to this minus the previous minimum plus 1. Where the minimum number you can reach is equal to minimum minus the previous maximum number plus. And how to do this inside the segment tree? You can't really do that. Technically, I'm not sure, like Am I missing something? How will you query that on a path? The vertices could have some LCA up there, right? We kind of didn't mention this case where the vertices are like having an LCA here. So it's kind of okay. We can go in this direction, but also we can go in this direction. That does not change anything as far as I know. But the LCA here, okay, the LCA, we'll find the LCA easily, it doesn't matter. Then there's two options. There's an option where the segment goes like that through the LCA, and there's an option where the segment goes only through one path to the LCA. Still, heavy light decomposition will can divide this path into like many multiple paths here, just making the problem a lot harder. So, okay, so we take whatever the maximum value we can reach here on this path. So there's something like that on this path. Like there's maximum here and minimum here, and you take the same idea here. Minimum, max. And now you would like to combine them somehow. Starting from the minimum point here, we could we could end up in any other point here. Starting from the maximum. Either I'm not seeing something or the implementation is hard. Let me just compare the standings, account standings. So he needs like 20 minutes to solve this. Not sure about it. So the case u equals 1, so the case where it's always the root one of, it's always like the path from a root node. Why is this easier? It's because you just want to find kind of still have this, but you can pre-calculate for each node what is the minimum and maximum value, and then you could do that. But here there's like many u's, so you can just like pre-calculate that. You will need to be able to shift these up and down. So how to do that problem? I don't like this. Like this LCA, okay, we can find this LCA, it's not a big deal, but this now you have to kind of have an account for when is this minimum reached and when is like a specific maximum reached. And combine them. Because we know this here will be reset to 0. But this won't. Yeah, it will be. So both actually, if you imagine this from LCA point of view, both actually start from 0. So there's some path here to U and there's some path to V. And if I draw the diagram, their axis is like this. Both start from 0 because we offset it. They go somewhere and they end up in U here. And in this way, it's the same. Let's say it's something like this. Okay, and now here it's a little bit harder to determine. In one way, if you go from the positive to the negative, from the negative to the positive, these are all -1s here, so you have like -1. So one of the graphs has to be somehow inverted for it to work. we could see, there is a way. What if I offset them? So this would be 0. So like one minimum would be 0. One of the diagrams would be inverted, but still works. So like one of the diagrams would kind of be inverted. So let's assume this diagram is inverted. Like that. So these are now -1s. Now this here point, let's say the minimum point is where you put both of these diagrams. You offset them by the minimum point. This is like how much I can reach. You offset them like that, so that. So that would be here equal to that. And from here, from the maximum point, you could easily travel to the minimum point and beyond, maybe. But then the idea is to do this from the maximum point as well somehow. Let's say like that. And now here it says that, okay, from the maximum point we could travel, but we could also It's definitely this way of calculating, but I won't code F1 because I'm not in the. I will certainly be able to code F1, but it's much more interesting to solve F2. Possible value. We kind of need LCA here because it's not the depth, it's just LCA. I mean, I don't know if this linearity holds with the query paths right now. It could be the case that given this LCA, you don't kind of do HLD, but you do something compared to this LCA. So maybe you don't even need HLD heavy light decomposition to compute this. We just compute the LCA of these, and then on the LCA then we do some magic with the minimums and maximums. Like, what if I have like a DP, and then this DP would be, what if I have some kind of square root decomposition? So like the following. If LCA is here, and I know for square roots of these what the DP kind of looked like, I could what do I need to do? What do I need to know? Know the LCA. I know U, V, so if I could know from the LCA how U behaves and how V behaves, so I know from U to the LCA, so I have like some DP, and then I have the last maximum and the last minimum, so I have like something like that, right? And then when I reach some point here, it's the DP of, so I know the maximum, the minimum, and like that, from to that point on, the minimum is updated. So the K here is updated. From that point on. Okay, so what if I have I'm not missing something, right? It's slightly changed. This, so the last minimum, the last maximum. Kind of want to build some other data structure on top of this, so like that. So let's imagine we have some path. Then from some node here, I know what is the last minimum node here and what is the last maximum node. And this here, let's say from this node, I know what is the last maximum node here somewhere. So this is like max, and this is max, and then this minimum. And then you just kind of wanna for this node, we want to know what is the last max node that is inside the path to the LCA, right? So nodes which is, if this is U, which are bigger than the LCA, like which are here, I don't care. Still not good enough. There could be actually only log n nodes. But no. So imagine this is 0, then first min max, second min max, third min max, no, this is linear. This is linear. If it was like a real competition, I would solve F1 really sooner, but now there's no point because both of the problems are like really different. The solutions for F1 is simpler. It's okay. When we find the LCA, what can we do? So we have essentially we have like something like this. Let's say this is the LCA. This is U and this is V. So we have like two minimum, two maximums, but this is not enough because, as we said, we could move it anywhere we want. So what does actually this say? So let's say this is 0, right? And this is something like a negative or this positive, doesn't matter. If I move all of these down to 0, but I have direction here. This is direct. That's the problem. I can't just start here and move here. I drew that a little bit bad. Maybe it's something like this. Then I can make this down, I can make this down, I can make this down. All of these that I can make down are some okay, can be anything because I can take from here and in here, and that would be. So that's my lower bound. So my lower bound is essentially what is this point? So some point P minus the last minimum, and some point P minus last at this point Pi. So some point Pi minus last of this point, last minimum. So last minimum of Pi, right? And now we need to find what is like the minimum of all of these on this path. That's not simple. Wait, how many souls? 58. It's not simple. So my solution was previously that I would invert this graph. I would have that somehow inverted. So I need to offset it by the LCA. Here by the value in the LCA. This graph also offset by the value in the LCA, and this will be like equivalent from traveling from U to V somehow. And now in this path, we need to somehow figure this out. We could also offset it by U, and then this will be 0, and then there will be like these. So what does that kind of, where does that get us? If I go from the maximum point, actually here this is last maximum at Pi. If we are making this minimum, we need from the maximum, from the last maximum point. So we somehow want to know This can be calculated. This can be also maybe inversely calculated. I would assume it can. So for each point we could have two values. One value is what is the minimum possible value in a subsegment ending at this point. And then the other one is the maximum possible value, and at this point as well. What's the minimum and the maximum possible value ending at this point? Then we need just to query out, but here this is like, how do we merge that? Like how do we merge that? Maybe you need to answer these queries in a smart way. If I have the minimum possible value till now, yeah, so from the LCA here we have the minimum possible value and the maximum possible value till now. And here we have the minimum possible value and the maximum possible value, and then if I want to achieve the maximum value, I would go from the minimum here. I will go until the maximum here, and if I want to achieve the minimum value, I would go from the okay, let's call it first LCA. I mean, we already have somewhere LCA, so I'm not to call this. Wait, I deleted. So here's the idea. Just close this down. We will go and we will say if depth at if. So first let's do LCA. I don't think heavy light composite, we do need heavy light. LCA JS is 0 if LCA dot depth dot, where's depth here? There's no depth in LCA. We'll just make it depth I will just use depth here because I want to remove HLD at the end. Depth at V is smaller LCA depth U depth at U swap UV and LCA UV. Now when we have LCA from UV, if L is equal to U, so if L is the vertex itself, I don't need to do any kind of merges, otherwise I do need to do some kind of merges. Okay, let's just comment out HLD for now, because we don't need that. Okay, the values here, the values we will last minimum is 1 and last maximum is 1. So when I add a value here, last min will, okay, the value of that node. The value of that node is, okay, this is the sum, but then there is some dp of that node. So this dp will be what is the minimum and what is the maximum possible node. So the minimum and the maximum possible node. For node 0, this would be what? One more probably, something like that. Here values, it's not defined for each node, so I will say so like I will just push back to that node. Also adjacency pushback empty array here as well. But last minimum pushback is, so last minimum is whatever the last so values push back at you. Last minimum should we do square root decomposition here? Because the last minimum should be until some node. sure. Oh, the camera froze or something. Yeah. I don't know. If I do square root decomposition, that means that this LCA will not only be, so how much actually F2 is, so there's a lot of number of events, so I'm not, I mean, square root decomposition will pass, certainly. Because the queries will be, so the queries can be like at most half of that, so that will certainly pass square root decomposition. What if I know in advance what will how they will, in what nodes there will be query for the LCA, and then if I know in advance, I will start from there like a new thing. But all the problems that there are linearly many queries. Well, there is some easy explanation to this problem. considering we have 512 megabytes, it is possible to be just square root decomposition. But I'm not sure even square root decomposition how to well implement it. It's a little bit hard to add. If I have some diagram like that, where I know what is the minimum, what is the maximum clearly, and I add something here, I mean not only the minimum, maximum, I kind of know like at each point, if I start somewhere, what is the minimum and maximum dp, so like that's how much I can go down and how much I can go up. So I kind of know this point, and now when I add here something, a lot of these points here should be updated. So a lot of these points will be updated, and so that's simple how. There are a lot of moving parts here, so I will leave that task maybe for later. So let's just revisit all the tasks. So here in this task we were asked to calculate the maximum possible cost of the coloring. So one can see that we can use, because maximum minus minimum, we want to somehow maximize this, right? So we want always choose the maximum numbers. So one color would be just to select like some minimum number and some maximum number, and what we can do is essentially select. Okay, so there are some elements, then we sort these elements, and let's say so we sort these elements like that, and what we can do is always we can pick a color here and a color here and do this like that. These will be the minimum elements in each of the colors. So this is the minimum, this is the minimum, this is the minimum, and these will be the maximum elements here in each of the colors. So n-half elements we will use the minus sign here. N-half elements we will use the plus sign. And this element here at the end won't be used. or if there is like an even number of elements, then we will assign color for each of them. This element will assign, of course, color, but even whatever color we assign, it won't be used. So that's problem A. Problem B was, so we're given some elements and you needed to select some sub array, then to like flip the signs, and then we wanted to end up with the maximum sum. So we could every time see that we could use some operations, like whatever operations we need, and flip all of them to positive numbers. And the sum is actually here the sum of absolute values. But the operations are a bit maybe tricky to count them. But what I do is, if it is a positive number and we are some in a negative segment, then we end up this negative segment up to here. And we say that we're not in a negative segment. Else, if it's a negative number, so if it's smaller than 0, and we're not in a negative segment, we have to start a negative segment from here, but we don't count it at the end. Now here that's like an edge case where at the end I just push 1 as like a positive number at the end of the array, but then I need to the answer -1 is just like this. I don't want to count that in the answer because I just added it here. It's just a trick to get away from like the rechecking here at the end. C is a very straightforward problem, sum in a binary tree. So we have some binary tree which is constructed in this level order way, and we want to sum up from the root node to some other node here at the end, or whatever here, let's say, doesn't matter. This tree could be really large, of course, but n goes up to 10 to the 16. And now the trick is, because it's binary tree, log n times you would at most sum up some element. Thus actually just summing up this element and dividing n by 2 is enough to get the next element here, the next element here, the next element here, and so forth. That's this, just simple loop. The apple tree problem was kind of okay problem. I don't know why they needed to complicate this with like pairs, but okay, whatever. So you were given some tree where the apples fall from some vertex u. So from, like, let's say the apples are here, so there's an apple here, it falls here, and it falls like either here or here, and then after here, like, it just ends up falling from the tree, right? So like it goes like that, or here. So for each of these vertices, you needed to say, you needed actually like to answer some queries, but for each query you had like two vertices, and then you needed to answer how many pairs of vertices do exist such that like the two apples can fall there. So by can I mean it's either that or that. So it's just a simple problem where you will need to count how many in each, like for each node in his subtree, how many nodes are leaves. So when you count this, then you just need to multiply the leaf nodes in the subtree of u times the leaf nodes in subtree of v, because this is combinations. U, the apple from the vertex u, will fall in one of these leaf nodes, and the apple in vertex v will fall in some other leaf nodes from the subtree of vertex v. There could be an intersection, but this intersection just we don't really care about it. Yeah, so this intersection is counted. E tracking segments, this is kind of an interesting problem in a sense of way that is very educational, but it could be very could be solvable in another way. I think I overkilled it somehow. So you were given some n and zeros. Then you were given also like these m, not necessarily different segments, so like these like segments that represent some subarray, and then now you needed to kind of like you had these q changes to the array, so flipping 0 to 1 q times through the array, right? Of course these changes are at most n. Okay, given these changes, tell me the first change after which at least one of these m subarrays becomes beautiful. And now what is a beautiful subarray? A beautiful subarray is where the number of ones is strictly greater than the number of zeros in this subarray. So we want to find some, like at least one of these segments turns beautiful. Now, I don't know, I probably overkilled it somehow. Maybe there's some like sorting, maybe there's some things, but what you could observe is if you like kind of reverse the problem, and instead of having the queries being queries, I'm just using the queries as like time points. What I'm doing here is actually I'm just saving all the intervals somewhere, and then I'm going through each of the queries, and then I'm adding like at this point, so this point has been changed in the ith query, and now what this creates, it creates this kind of timeline. So this point is changed in query 1, this point is changed in query 2, this point is changed in query 3, and so forth. And now we just need to some way of like calculating whether there is a segment, so some segment which is this, like these intervals that we saved earlier, whether like there is one interval where the median, so like the median here, so if I just take all of these numbers in this interval and sort them out, so like 1, 2, 3, 4, and 6, the third query will kind of have like three ones here. So this third query will have these 3 ones here, and thus making this subarray beautiful. And since we have m subarrays, we need m times to query some segments, and what I want to do in all of these intervals, I want to query from L to R what is the kth element, but the k is equal to this median plus 1 element. So what is this? So what is this element? So in other words, in what query does this element change in this subsegment of the array? And then the answer is the minimum of all of these, of course. And if the answer still remains int maximum, it's -1. It's answer +1. This is because indexing of the queries. Another way to there are multiple ways to do this k thing, but because we don't kind of need dynamic changes, it's just this query. This is like from geeks to geeks, from geeks for geeks. This already like this called wavelet tree, the segment tree, where you merge these kind of arrays, and then you just take a look at this takes upper and lower bound, just this very common thing. Yeah, there might be another way to do this. Also pay attention that here that a is set to int maximum, so if a query has never occurred at this element, so if here let's say this element was never changed here, and let's say this element was never changed, and let's say this element was never changed, so like all of these are ones at the end, but all of these are ones, but this remains 0. So these are somehow changed to 1. What we want to do here is make these zeros have an int max query time, and thus when we sort, this will remain at the end. And if there are many zeros at some subsegment, so let's say that we have something like this, where we have like 0 0, let's say 1 0 0. All these are int maxes, so this is max 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 max, and this is like the first query here. If I sort them, there will be like 1 max 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 max, and thus when sorted, when we take a look at this middle number here, this middle number will be int max as well. So it goes like this. You don't have to have edge cases here. Just this is by default like taken care of. This is F. Now this is E. Then F. I don't know. I mean. There could be a very easy solution for F. Like the F1 is very, straightforward. You kind of want to know for each node, you want to know the dynamic programming for the last, because each query is from the U node, from the root node to some node V here. This can be imagined as some prefix. So we will do some prefix here. So like this. Let's see. So we started 0, or actually we started 1, the U node, and then when we add 1, we go 2, and then 3, and 4, 5, and then you reach something here, which is maximum. And then you kind of reach minimum here as well, like this. But so from to the V node, we only want to know two values. We want to know what is the minimum ever reached to this V node, and what is the maximum ever reached to this V node. The minimum here we can ever reach is some maximum which is prior to some node. If I'm at this node and I have some value, let's say -100, and this maximum node here is like 300, then this node here has then the minimum will be 300 minus 100, which is 400 here. -400 here we can reach, because if we start here, we can go 400 down, and the maximum node here at this point is, well, the maximum node is not updated, because here somewhere it will be updated, because let's say that this is some minimum here, and when we reach this node here, let's say that the previous minimum is 0 or 1 actually, and here we reach like 200. Then yeah, of course, 200 will be this way, like 199 or 200 or whatever will be this difference here, this reach. So 200 will remain 200 from this, and you can do this with simple DP here, because U is fixed. For each node V, we will have two values of these. And when we have these two values, K must hold this equation. This is for F1, but for F2 is very, very hard. I mean, it's harder than I don't know. If only 100 people solved it, I kind of have multiple ideas here with the LCA and like having square root decomposition. So like remembering these like states changes on square root levels, and then like recreating these fast enough. But this is just too much implementation for me, and I don't kind of want to do that. let me just see if I can I see this? So yeah, he's using LCA, he's doing some accumulation. Here he's calling some combine function which combines which essentially he's doing an LCA jumping, and we want to solve. Yeah, here is like doing this and combining it again. Yeah, the same thing we did with saving these queries at the end, just using first this, and then he's doing these nodes, combining the D. So he's actually doing some sparse table here. That's like a sparse table, and then this sparse table is like, yeah, so I see. So this sparse table is the same thing. We talked about with the same solution for F1, with like starting from U. Now imagine like starting from here and from here and from here, from each of these. But this is like a sparse table. Now the combination of this, how to combine them is not it's not that straightforward actually. But I will break down this maybe in some other video. So subscribe, check out my channel for more, and I'll see you in the next one.